We are moving to a new chapter. Finally, we are done with all of chapter 9 of Infinite Series. And what we have really for the rest of the course is now we have a bunch of just short topics where we'll be able to spend about a week at a time looking at a few topics that are all connected in some way and then take a quiz over those. So you will not basically experience what we have over the last few weeks. So our next chapter, it's hard to even call it a chapter, kind of like a mini topic, is going to focus on differential equations, which is a chapter that we covered back in Calc 1. It was chapter 6. So I just want to start by just giving you an overview of basically what we've done in AB last year and where we're headed in BC. So in AB, some things that we did in the differential equations, the primary thing we did was the very first bullet point. We worked with separate and integrate. We were looking at differential equations, just to give you an idea, it would be something like dy dx equals x over y, something like that, where it was a differential equation that was in terms of both x and y. Our job was to separate and integrate. We did a lot of cross multiplying. It was very algebraic so that we could come up with a general solution. That's what GEN, general solution. And then we used conditions like, for example, when x is 1, y is 5 to give us our C value and get particular solutions. And we spent, I would say 75% of that chapter was focused on that skill set, whether you had initial conditions or you're just keeping it generic. We also did slope fields in that particular topic. Slope fields were a visual representation of a function. So basically each point we drew a little mini slope that represented what would the slope be of the graph at that particular coordinate, and we drew that, and the idea was that gave us an overall shape of the general solution. And then the other thing we did that was more of a review than anything else is we talked about how differential equations were one of the ways that we could solve exponential growth and decay problems. Exponential growth and decay is when a quantity is growing or decaying at a rate that's proportional to itself, so proportional to how much that we had to begin with. And we use this formula, y equals c e to the kt. And most of that lesson was truly a review of what you did in Algebra 1 and Algebra 2. So here's where we are in BC. Really, there's only 3 new pieces to add to this. I'm not going to go back and do a lot of the AB stuff at all. I will talk a little bit on exponential growth in the next lesson just because it ties so closely to where we're headed, but you won't really see much in the slope fields and separate and integrate. First, we have to do something called Euler's method for approximations. Euler was a mathematician. We know him because he came up with the letter E. He has a method for approximating a function that actually uses slope and differential equations. We're going to do that today. Not super exciting, but very easy. And then we get to my favorite parts of the topic. We're going to do Newton's law of heating and cooling. This is the idea that how quickly something either warms up or cools down is directly related to the difference between its temperature and the temperature of its surroundings. So, for example, if I take a hot cup of coffee out on a winter's day, it's going to cool a whole lot faster than if I take that same hot cup of coffee out in the summertime, where you don't have a big difference between the coffee's temperature and the surroundings temperature. I like that lesson. It's something that we can all relate to. And then the last one, which is incredibly ironic given our current situation, we're going to talk about logistic growth model and the idea that things grow exponentially to a point, but there is also a cap. We have what's called like a carrying capacity, that things can only grow to a certain point. Like a population can only get so big because our environment can only support so much. But this one, we talk about viruses spreading, rumors traveling, both of which are happening like crazy right now, and talking about what's the threshold there? When are these things traveling at the absolute fastest? What's the cap with that? So those are the topics that we're going to do in this particular chapter. So we're going to start with Euler's method. So let me give you a little rundown on what it does. A lot of times it doesn't make a ton of sense until you actually see examples. So we'll do examples. Euler's method is a numerical approach to approximating the particular solution of a differential equation. So slope fields were a visual way to approximate a solution. Euler's method is going to be more of a numerical or arithmetic approach to approximating. If we know an initial point, so this a sub 0, y sub 0 is like our starting point to make this approximation. The approximation will weaken as you move away from the initial point, which shouldn't shock you. It's the same idea we had with series making approximations. Now, this next part, I want to show you a visual here in a second. Your approximation will be above the actual value if the function is concave down, and below if it's concave up. So let me show you a picture, and then I'll come back to this. So here I found this it was a website or a textbook, and I thought this is something better than what I could do. I wish Delta Math did it so they could see it as well. So your blue curve is your basic unknown function. It's your function that we have like a differential equation for. And then your pieces that look like little like partitions, we have the A pieces. That's an Euler approximation. So that's doing an approximation. We start with this original value, which is going to be perfect. And then we're going to use slope and our next x value to get this next point. And then we're going to do the same thing. And we're going to kind of build this approximation. And notice as I go away from the initial point, there's more distance between my actual and my approximation. So I am weakening. So the concavity piece, because this graph is concave down, as I draw this approximation, they call it a polygonal approximation because it's made up of these little small sides, these small pieces, would be actually above the actual function. And then you notice in the picture on the right, you have your blue curve again. This time my Euler's method, my little segments are this green segments, and you'll notice that my approximation is below the actual. And again, it's spreading out more as we go further away. The approximation really isn't becoming nearly as useful. So that's what I mean by the approximation is above if it's concave up, or concave down, excuse me, and below if it's concave up. Now we are going to get into examples. I think I'll put that actually in a separate video, do all the examples in one video, but I do want to give you an idea of where you can go to kind of read a little bit more. If you're listening to me going, okay, I don't get it, I'm obviously going to do examples. If you still want to see more for pictures, for more examples, in the Barron's book, the new edition that I had you guys get, if you go to page 365 to 369, it has an entire section on explaining the process, and it also has an entire section on with just examples with it. So I'm going to give you a little bit more, and then we'll do a separate thing with examples. So to do this, to do an Euler approximation, these are the things that you'll be given. They have to give you a starting point. They have to say we're starting at the point 1, 5 or negative 3, 2. That is your initial point or your initial condition. They have to give a differential equation that's going to model this function, that's going to tell us about the slope of this function. And they also have to give us something called a step size. And your step size is how far apart are we making these approximations. So if you look at your pictures, so how much distance is happening between these 2 point approximations. Usually we work really small steps. You'll have steps that are maybe 1/10 of a unit. A lot of them we do a half, like a 0.5. They have to tell you that. They have to tell you how many of these approximations are you making, and basically how far are you getting? What's the goal? How far out from the center do you need to make this approximation? And then on the right, and this is something you want to jot down to just kind of get the pattern in your head, and this is very much a pattern-based problem. In order to make your approximation, you're going to start this pattern. You're going to take your original y value, which is your y sub o. So you're basically just taking this value here, y sub o. And then to it, you're going to add your step size. So if your step size is a half or a fourth, you're going to take that times what your function actually, your derivative, what the derivative is at that initial point. So this right here is plugging into the derivative. So this is plugging into the differential equation. When you do that, you're going to get your next y value. So you're going to get that next step. You're then going to take that y value and start over. Same pattern, you're going to take that y value plus your step size times your slope value at that differential equation to get your next y value. And you're going to continue this pattern until you get to where you need to make a prediction. So, and you will know how far you need to go to make the prediction. And so this is just kind of showing that this pattern continues. So that is, again, Euler's method. We have this initial point. We're going to be using the starting y value, and then we're going to add to it the step times the derivative at that point. Get a new y value, and then you keep going. And it's very methodical. It's very much a calculation. So having a calculator close by, I'll show you some that you don't need it, but a lot of them you will use your calculator. So that's the basics. I'm going to do the examples in my next video.